Hello everyone, welcome to our discussion of section 6.6 where we will be talking about improper integrals as you can see it on the screen. Now we've talked about integration where there is no limits specified or indefinite integrals and where we end up with a constant term plus c. We also talked about definite integrals of various kinds. Now, improper integrals are integrals where at least one of the limits of integration is set to infinity. Now, it can be the upper limit, as you can see immediately on the screen, or it could be the lower limit set to minus infinity, or it could be both limits of the integration set to minus infinity to infinity. So in cases like that, let's begin our discussion by looking at the case where the top limit of the integration is set to infinity. In such case, we will take the limit of the integral, we will replace the infinity part of the interval, interval of the integration with a constant. Your book uses the variable t. Just to be consistent with your book, I'm using t. You can use this to be any other variable, but we normally use u for substitution, u and v for substitution, especially when we discuss integration by parts, and x is the normal interval of integration. So I'm guessing that's why your book, the author of your book, chose t as the variable for when we take the limit of an integral. So these are, by the way, all these cases that I just mentioned, where when the top limit, the bottom limit, or both limits of integration are set to infinity, these are type 1 of improper integrals. So that's when type 1, because there are two types, we will look at both with examples. So type 1 is when the integration takes place over an infinite interval along the x-axis. Of course, any one of these, a to infinity, minus infinity to b, and minus infinity to infinity, these are all infinite intervals along the x-axis. So type 1. So with respect to type 1 of improper integrals, if the top limit is infinity, then we replace that top limit with the variable t, and then take the limit of the integral as that variable t approaches infinity. Now, if this limit exists, we call that this integral, the initial integral, is convergent. If this limit does not exist, we say that the original integral is divergent. Now, how do we know if the limit converges? Well, if the limit exists, then we should have some value, right? Some value of any quantity. If the limit exists, we say that the original integral is convergent. But if you take the limit and you end up with either plus or minus infinity, then we say that the original integral is divergent. In other words, there is no solution for it. Saying divergent means there is no solution for it. It's just that area that is represented by that integral just keeps getting bigger and bigger and bigger. So if the bottom limit is set to an infinite value or infinity, then we replace once again, we replace that infinity with the variable t, and then take the limit of that integral as t approaches negative infinity. Once again, if we are able to quantify this to a certain value, then we say that the original integral is convergent. It's converging to a certain value. That area between the x-axis and the curve, that is f of x, is approaching some quantity. But if this limit does not exist, then we say that that integral diverges. So that area is just expanding infinitely. There is no value to which it converges. It's just diverging. It's an infinite area value. And of course, if we have this case, going from negative infinity to infinity, then we can break this original integral up into two segments, one from negative infinity to a, and then plus a to infinity. For this a can be anything in the interval from negative infinity to infinity, but for the sake of convenience, as I mentioned it here, for convenience, we usually take this a to be 0. So minus infinity to 0 and then 0 to infinity, we would break up this original integral into those two pieces. Okay, so having said that, and then after we do that, we will then use this method and that method to take the limit of each integral and find out whether we have a convergent or a divergent integral. The thing about this, breaking up the integral into two pieces, is this, that if any of these two pieces diverges, then the whole thing diverges. The whole integral diverges if one of these diverges. But if you consider this one, and if it converges, then you also have to consider this, calculate this, and make sure that it converges in order for the original integral to converge as a whole. But if one of these pieces is divergent, then the original integral is also divergent. So you don't need, if you check this and if it's divergent, you don't need really to check this one to see what this is doing. If that's divergent, the whole thing is divergent. Okay. All right, so let us go through some examples. Oh, before that, so your book mentions this, so I should mention it too, that if you have an integral of this form, then you don't need to go through that exercise that we just talked about, taking the limit. If you have an integral of this form, which of course is improper integral of type 1, because one of these limits is already set to infinity, then this integral is convergent if this power is greater than 1, and divergent if p is less than or equal to 1. I mean, you can, this makes a lot of sense, because if you just try different values for p that are greater than 1, you'll see that this fraction, this ratio, gets smaller and smaller and smaller. So of course, if that quantity is getting smaller, then taking the area over values that are decreasing and decreasing to infinity, then we expect the whole thing to converge. But if this p is less than or equal to 1, if you just take on your calculator, if you test some values that are less than or equal to 1, you'll see that this quantity just gets bigger and bigger and bigger, particularly when you try some p values that are negative. Then this quantity gets to be very large. So this is based on that ratio. Okay, so having said that, let's do some examples. Suppose we want to determine whether each of the following integrals that we're going to go through is convergent or divergent. And if it's, of course, if it's divergent, we won't worry about finding any value or evaluating the integral. But if it's convergent, we want to evaluate that integral. Okay, so here's one example. Suppose we want to evaluate this integral going from 1 to infinity of 1 over 2x plus 1 cubed dx, right? Clearly, this is the improper integral of type 1. The upper limit is set to infinity. So right away, we can set this to, we can take this limit, set this infinity piece to t, and then take the limit of the integral as t goes to infinity. So let's do that. Limit as t goes to infinity of 1, integral of 1 to t of 1 over 2x plus 1 cubed dx. Now, this is a very easy ratio to calculate the integral for. Maybe I should use a scratch paper here. So that this piece, we can rewrite it as, so this is just my scratch paper, 2x plus 1 to negative 3 power, right? We can rewrite this ratio as that. Now, if we want to integrate this, we learned a long time ago that we can just add 1 to this power and divide this whole thing by the new power. So if we do that, then we get, so 2x plus 1 negative 2 divided by negative 2, right? But if we had this to begin with, to find the derivative of this, we would have had to multiply the result of the derivative of this when we obtain this by 2 inside the parentheses because of the chain rule, right? So because of that, we will need to divide by 2 in order to get rid of that. So this would be minus 1 over 4 times that. So we would end up with minus 1 over 4, and then putting this in positive power form, we'd say 2x plus 1 squared. Okay, so let me just transfer that to my paper here. So we have limit as t goes to infinity of minus 1 over 4 times 2x plus 1 squared. Of course, this is going from 1 to t. Okay. All right. So let's just evaluate this quantity. What do we get? We get limit as t goes to infinity. And we have, replacing x with t first, we have minus 1 over 4 times 2t plus 1 squared. And then minus, replacing x with 1, we get 2 plus 1, 3. 3 squared is 9. 9 times 4 is 1 over 36. Okay, so it's clear that if you now take the limit of this quantity as t goes to infinity, and t is the only place where t appears is right here. So this denominator is going to become very, very large, and minus 1 divided by an infinitely large quantity is just 0. So this term is equal to 0 as you take the limit of it as t goes to infinity. So we can say 0 minus, so that's plus 1 over 36, and this will lead to 1 over 36. So notice that this quantity is not equal to plus or minus infinity. So therefore, or thus, the integral, the original integral, so the integral, and I'm going to write it, the integral from 1 to infinity of 1 over 2x plus 1 cubed dx converges. Okay, which is what they asked us to do. Find whether that integral converges or diverges. So the only case where the original integral diverges is when this quantity is either plus infinity or minus infinity. And we're clearly not that. Okay, let's do another example. So suppose now we want to, as another example, we want to find if this integral, this clearly improper integral, right? The bottom limit of the integration is negative infinity. That this integral, whether it converges or diverges. Okay. So once again, we go by taking the limit of this, replace this negative infinity with t, and take the limit of the integration as t goes to negative infinity. Let's do that. So limit. By the way, I keep forgetting to mention this, but please feel free to pause the video. Don't spend more than 15 minutes on coming up with your own solution, but it's very important that you give these your own thought before you see my solution. So please do that before you unpause the video. Okay, so I'm assuming you've done that and now you're back. So hopefully our answers agree. So as t goes to negative infinity of the integral from t to 0, 2 to the r dr. Okay, so recall, as we try to integrate this, recall that we had a formula, right? That if we have some integral exponential of an exponential function a to the x, a basic exponential function, right? A to the x dx, that is equal to that exponential function a to the x divided by natural log of the base. And of course plus c if it's just an indefinite integral like that. But in our case, we don't need the c because we have t and 0. Nonetheless, we can apply this to the integrand here. So we will get, if we do that, we will get, and I will put the limit here, limit as t goes to negative infinity of the whole thing, the exponential function 2 to the r, divided by natural log of the base, natural log of 2. And so, of course, this is going from t to 0. Okay, so let's evaluate this quantity then. We have limit as t goes to negative infinity of 2 to 0 divided by natural log of 2 minus 2 to t power divided by natural log of 2. So of course this is 1. This whole thing, this numerator is 1 divided by natural log of 2. And then, so let's, as we do that, as we simplify this expression, let's apply the limit as well. So we get, what do we get? We get 1 over natural log of 2. We apply the negative infinity. This is, the power is negative infinity. So minus 2 to negative infinity divided by natural log of 2. All right? Then what? Do you see where this is going? This is a negative infinity power. So let's put this in positive infinity power. So what do we get? We get 1 over natural log of 2 minus 1 over 2 to positive infinity times natural log of 2. This is just rewriting this with positive power. Then this denominator is getting extremely or infinitely large. So any number including 1, divided by an infinitely large number is just 0. So this term drops out. So we get 1 over natural log of 2 minus 0. And therefore we get 1, the final result is some quantity, 1 divided by natural log of 2 and therefore, so as you can see, this is not equal to plus or minus infinity. Therefore, or thus, the integral, the original integral, right? The original integral negative infinity to 0, 2 to the r dr converges. Okay? So that represents some area quantity. All right. So let's do another example here. I hope this is making sense and making it easier for this subject to be understood. So let's do another example here. So suppose we want to find if this integral, if this improper integral is convergent or divergent. Okay, so you might remember that when we had something like this with exponential function times the variable, we used to use integration by parts, right? It's very effective for integrating integrals like that. So let's do that. Let's break this up, and then we'll, of course, because of it's an improper integral, we'll have to take the limit of each piece of the integration by parts. Okay, so we're gonna well, why don't I just say take the limit right now and then apply the integration by parts. So limit as t goes to negative infinity of t to 6 r times e to the r third dr. Okay, all right. So now using integration by parts, so we take the easier piece as u. So u, let's take u to be equal to r. So that means du, it's going to be dr, right? Dr. And then so dv, we're going to take e to r divided by 3 dr as our dv. And therefore v, the exponential function to base e is easy to integrate because the derivative of this is itself, except that by the chain rule we have to watch out for this 1/3. So we have to multiply this by 3 e to r divided by 3. Okay, so now when you take the derivative of this expression, it'll be e to the r over 3 times 1/3 by the chain rule, and 1/3 and this 3 cancel each other out, and we get dv equals e to the r over 3 dr. Okay, so now that we have that, let's put it together. We have uv, first of all, so 3r e to r divided by 3, and I didn't leave room for myself to put the limit So let me do that here. Limit as t goes to negative infinity. Sorry about that, but I tried to fix it there. So that like that. And then, so that's the limit of that piece, which is uv. Of course, and this is the limits of integration are t and 6, t to 6, minus v du. So we have, since this 3 is constant, I'm just going to put it outside. And then we have, well, I didn't leave let me do it this way. Since this limit, I need to put that here as well. Since I forgot, I'm just going to put that inside, the whole thing inside the parentheses. That way, this limit of that expression as t goes to negative infinity applies to everything that's inside the red parentheses. Okay, then I don't have to make a mess of this. All right, 3 and du, which is dr. So we have e to r over 3 dr. And of course, these limits are t to 6. And then I'm going to close this red parentheses. Okay, I think that should do it. Yeah, so this is minus infinity. All right, so now let's this one is already done, but before I apply this limit and calculate this integral, I want to integrate this piece too. So what I want to do is limit as t goes to negative infinity of, I'm just going to keep this still the same for this time around as well. And then let's integrate this. This will be minus 3 times 3e. That's an easy integral. So this 3 is that. And then times 3e to the r, or r divided by 3 t to 6. Okay. And we have the limit outside here. Okay, now let's evaluate these quantities and then take the limit afterwards. So to do that, we have limit as t goes to negative infinity. So this will be 6 times 3 is 18. 6 divided by 3 is 2. So we have 18 e squared, and then minus, now we have to take the 3t, right? 3t e, 3t times e to t divided by 3. And I will just put a bracket on that, and then minus 9. So minus 3 times 3 is minus 9. And then, so minus 9. And then 6 divided by 3 is 2 again, e squared. And then minus that we would have here, we would make this positive 9 e to e to t over 3, like that. Okay. And then let me close this like that. So this minus is, I already distributed this minus into this result. That's why you have minus and then plus. Otherwise, you would have minus times that, and then minus would be positive again. So I already distributed this into this result. All right. So now let's take the limit of this quantity. What do we get? This one stays the same, right? So 18e squared. Now, this one is an interesting case because you have a t here and a t here. So negative infinity here times this negative 3, it'll be positive infinity. But this negative infinity e to, well, let me use my scratch paper here. When we replace the t for this quantity with infinity, notice what we get. So we get positive infinity times e to minus infinity divided by 3, since t is going to negative infinity. Now this quantity, the question is this quantity approaching positive infinity faster or negative infinity faster? Well, it's approaching negative infinity. Let me rewrite this. So infinity, that one, times, put this with positive power. We get 1 over e to positive infinity over 3, or infinity. Positive infinity over 3 is just infinity. We can just ignore the 3. So we get something like that. Because the base here is 2.718, that irrational number, this quantity is approaching faster, is approaching 0 faster. This quantity is approaching 0 faster, a lot quicker than this quantity is multiplied by infinity. So this quantity as a whole is approaching 0 much faster than it's growing because of this infinity multiplier. So ultimately, this will go to 0, this whole quantity. Okay, so as we take the limit of this quantity, we'll have minus 0 or positive 0, and then, which makes no difference. And then minus 9, the limit will not affect this, so minus 9e squared. And this one also approaches 0, right? By the same rationale that we used here, except that here we don't even have a t. So you can write this piece using my scratch paper here. So using that, you can rewrite it as 9e to minus infinity divided by 3, or 9 divided by e to infinity, because just ignore 3, right? And this quantity is approaching 0. So plus 0. So what we end up with here is 18e squared minus 9e squared would be positive 9e squared. Right? So this quantity, of course, is not equal to plus or minus infinity. Thus, the original integral, which was negative infinity to 6r times e to r over 3 dr, converges. Okay. We will see cases where it's divergent, but so these are the exercises that I picked at the end of the section 6.6 from exercises, and at random I picked these up, and they all seem to be converging. But there are cases for sure where the answer will be either positive infinity or negative infinity, and the original integral will or diverges. Okay, so let's do another example. Suppose we want to determine if this integral from negative infinity to infinity diverges or converges. right? Like that. So, as we mentioned on that first slide, when we have cases where the limits of integration are from negative infinity to infinity, we want to break this up into two integrals. And for convenience, we choose that the two pieces to go from negative infinity to 0 and then plus 0 to infinity. Let's do that here. So we have negative infinity to 0 of x squared divided by 9 plus x to the 6th power dx plus 0 to infinity of x squared divided by 9 plus x to the 6th dx. Okay? So notice that in this case, the integrand is even, right? It's an even integral. So it's which means it's symmetric with respect to the y-axis. This is something we learned in pre-calculus. So let's just recall that because the integrand is even, and that has a nice simplifying impact on what we're doing here, just recalling that. Because this integrand is even, i.e. symmetric about the y-axis, right? We can rewrite this, the above expression. So we can rewrite the above equation as simply 2 times this integral, 0 to infinity of that. Okay, so we can rewrite that as 2 times the integral from 0 to infinity of x squared over 9 plus x to the 6th dx. Okay. All right, so then looking at x squared and x to the 6th, notice that just if we use the substitution, if we just say, so this is the improper integral, for sure we'll have to take the limit of this at some point. But before that, just notice that this is simply, if we take this as, because recall this identity that we used in section 6.3. So recall, I guess I should write it at some point here, but recall that if you have integral, let me move this up a little bit. If you have integral of dx over x squared plus a squared, this is equal to 1 over a, and this a squared could be here or here, it doesn't make any difference, but this form, it'll be 1 over a times inverse tangent of the variable over the constant plus c. So I just wanted to briefly mention this because remembering that it's helpful if we can write this denominator as a perfect square, so x cubed squared. So let's do that. So taking u to be 3, well, let's see, taking u here to be x cubed, or let u to be x cubed, and then therefore du is going to be 3 times x squared dx, right? And compare this with that, with the numerator. All we have to do to replace that, to use this substitution, would be to just say 1/3 du, right? 1/3 du, 1/3 of that will give us x squared dx. So let's do that. So then we have, and meanwhile I'm just going to stop writing the limits of integration for now, and then at the end I will put them back. But for now, let's disregard these, and then we have 2 times, let me not forget that 2, so 2 times 1/3 du divided by 9 plus u squared. Okay, so that's that. And then, so this, then it seems that we have to make another substitution here. So if we get 3u, okay, so let us take u, that one, to be equal to 3v. So what would that give us? So this will give us du equals 3 dv, right? So 3 dv, and then 3 dv, so du equals that. So let's replace this, replacing again. We have equals twice the integral, so du is 3 dv, so 1/3, so 1/3, I'm just replacing the du with 3 dv, like that, and then the denominator 9 plus, instead of u squared, we have 3v squared. Okay, so that would be 9v squared, and then we can factor the 9 out. Okay, so let's do that. So by the way, this 3 and this 3 cancel each other out, these two, and we end up with 1 over, okay, so let's do that. So we have 2 here, and then this 3 and this 3 cancel each other out. We end up with 1 over integral of dv divided by let's see, so 9 plus 9v squared. So we're working our way toward obtaining this format, because if we do have this format, then we can easily integrate it using this formula. So this is our objective as we manipulate this original integral. So now we got it, almost we got it, right? dv, see, dv dx, so nothing in the numerator, the denominator has to be 2 perfect squares added to each other. We're actually there, but we can factor out 9. So we can say 2 times 1 over 9, and then dv divided by 1 plus v squared. Okay, now I'm just going to put that statement here, that recall from section 6.3 that integral of dx over x squared, I guess, from x squared plus a squared is equal to 1 over a times inverse tangent of the variable divided by the constant plus c for the indefinite integral. But we do have limits of integration, so we won't be using the c here. But now let's apply that to that. So what do we get? We get so from that we have 2 over 9 2 over 9 and then times, in our case, this is the variable v squared, right? A squared is just 1 squared or 1. So 1 over 1 is 1. So we don't need that piece because it's just 1. And then tangent or inverse tangent of x, which is v, over a, which is 1. So v over 1 is just v, or v. Let me write it like that. Inverse tangent of v. Okay. Now, we made several substitutions, right? We substituted x cubed with u. We had that substitution, and then we had this substitution. So we have to go back to x. Okay, so let me do that, and I don't think I can fit it all on one page here for sure. So let me go to the next page. So so we're gonna, because u was set equal to 3v, then v is equal to u divided by 3, right, from this. V would be equal to u divided by 3. So let me replace that. So I guess I can put one more line here. 2 over 9 times inverse tangent of u, instead of v, we have u divided by 3. Okay. Next step, we're going to have to go from u to x. So let me bring this back down again. U was equal to x cubed. That's what we chose. Therefore, let's rewrite this. 2 over 9 times inverse tangent of x cubed divided by 3. Okay? All right. So I might need this slide again, but for now I'm just going to set it aside. Now that we have this, therefore, thus, the original integral can be written as follows. So I'm just going to say 2, this is what we had, 2 times 0 into infinity of x squared over, this is before all the substitution. We went from that, we found the integrand, but now we have to take the limit of this as t goes to infinity. So we're going to have to replace this infinity by t. So let me, so this would be, and then so, by the way, that 2, this 2 is already included in that. It's already part of this 2 over 9. So, so this is equal to 2 over 9 limit of as t goes to infinity of tangent. So t would have been here, and then limit of this integral as t goes to infinity. And so limit as t goes to that of this integral that we found, which is inverse tangent of x cubed over 3, of course 0 to t, right? So 0, 0 to t. Okay, so now let's evaluate this integral, or this quantity. We have 2 over 9, and then limit as t goes to infinity of inverse tangent of t cubed over 3 minus, we really don't need for the limit of that for 0, so minus tangent, inverse tangent of 0 cubed over 3 is just 0, right? So it's just this piece that we really need to take the limit of as t goes to infinity. All right, so now if we do that, we can replace this with 0 right away, but before that, let's substitute this with infinity. So what do we get? We get infinity, right? As we take the limit, so and 2 over 9 is outside here. So as you take the limit of this quantity as t goes to infinity, this inside, let me actually write it out. So that becomes infinity minus inverse tangent of 0. So the inverse tangent function, I don't know if you remember from the, let's just recall. If this is the xy axis, then the inverse tangent function is like this. This is the inverse tangent function. Inverse tangent function. What it goes, it ranges, its domain is negative infinity to infinity. The domain of the inverse tangent function, sorry, I was a little bit off the screen. I apologize for that. So the domain of the inverse tangent function goes, let me write it here. The domain goes from negative infinity to infinity, as it's shown in this picture. But the range goes from negative pi over 2 to pi over 2. So this is negative pi over 2, and this is pi over 2. This horizontal line is pi over 2, and this is negative pi over 2. And these are asymptotes, horizontal asymptotes, okay? So that's important to remember from trigonometry. Now, because of that, then the range, this range, because we were integrating over the positive values. Over the positive values, we know that the inverse tangent of the domain, as domain goes to infinity, the inverse tangent approaches pi over 2. Right? It approaches pi over 2 as the domain of inverse tangent goes to infinity like that. We're getting closer and closer. The value of the inverse tangent gets closer and closer to pi over 2. And that's the scenario we have here. So therefore, 2 over 9 times this we can replace by pi over 2. This whole thing is pi over 2. And of course, from the same figure again, if we remember from trigonometry, math 127, inverse tangent of 0 is 0, right there. It's 0. So then minus 0. Okay, so then basically after that we can simplify, and 2 and 2 cancel, we get pi over 9, right? Pi over 9. So definitely this quantity is not equal to plus or minus infinity. Thus, that original expression, let me write that down. Thus, this quantity, negative infinity to infinity of x squared over 9 plus x to the 6 dx converges. Okay, so converges. Okay, so like that. All right, so oftentimes we need to revert back to what we learned in previous sections or previous classes. So that's very typical of solving problems here in calculus. And that's why I always refresh my own mind by going through my previous classes' books. So that way I can remember those easier. All right, so let's see. So we did that example. We went through that one. All right, so maybe we should start the new type 2. We should talk about type 2. This was type 1 when one of the limits or both were infinity or indefinite limits. So 0 to infinity or negative infinity to some quantity. So now type 2 of improper integrals, this happens when we have some kind of discontinuity over the interval of integration. Okay, so the type 2 stems from the fact that there is discontinuous integrals and we know those as vertical asymptotes. So integrals, and this is page 7, I guess. Yes. Well, actually, let me, so I do have a prepared slide for that. Let me, so this would be that. So let's call this page 7. All right. So type 2 is discontinuous integrals. That is integrals over an interval that contains a vertical asymptote. So far, every integration that we've done we could do that because the function was continuous over the interval of integration. And that's how we were able to calculate the area under the curve over that interval, which we call integral. But here, what if we have a discontinuity in the interval of integration? So this is type 2 type of improper integral. So this is one case, case A. Suppose that the right side, we have a vertical asymptote. We have a vertical asymptote on the far right-hand side of the interval of integration, or the upper limit of the integration is a vertical asymptote. If that's the case, then once again we take the limit. We substitute the quantity for which there is a vertical asymptote in that interval, and we take t not to go to infinity or negative infinity this time, but t should go to that quantity for which we have a vertical asymptote. Now, because in this interval of integration, we can only approach b from the left side, so it's important that we say t as t approaches b from the left side, because we cannot approach this end or this asymptote from outside of the interval. We're only integrating over this interval, so we can only approach the asymptote, which is b, x equals b, from the left, right? and that's reflected here. T approaches b from the left side. Okay? Then we evaluate that integral. And if the limit exists, if this limit exists, as t approaches that vertical asymptote quantity, or x equals b, if this limit exists as x approaches b, or t approaches b, then we say that the integral, the original integral, is convergent. Otherwise, we say that it's divergent. Now, case B is if the vertical asymptote was on the lower limit of the integral. Not on the higher limit, but the lower limit on the left side. In other words, here, we can never be, the x can never be a because we have an asymptote there. So this time, x equals a is a vertical asymptote, the lower limit of the integration is. So this time, we replace a as t approaches a from the left or from the right. What do you think? T can only approach a from the right. It cannot approach it from the left because that would be outside of the limit of boundaries of integration, right? So that's reflected in that plus. As t approaches a from the right side, we take the limit of the integral as t approaches a from the right, and if it exists, if that limit exists, then the integral is convergent, and if it doesn't, it's divergent. And we know what to look for, right, as we take the limit. If we end up with some quantity that we can understand, which is not equal to plus or minus infinity. If it's not equal to plus or minus infinity, then it's convergent. But if it is equal to plus or minus infinity, then it is divergent. So that's second case. And then third case is that if we have a discontinuity not on the right, not on the left, but in the middle of that interval. In cases like that, then we'll have to break up the original integral into two pieces. So one piece would be that, going from, so C, as you can see in this picture, so from, well, I should actually label this. So this would be A, and this would be B. So C is between A and B. And that is shown here, by the way. So C is between A and B, somewhere there. And if that's the vertical asymptote, then A to C should be one piece, and then plus C to B would be the other piece, or the other integral. Now, as before, as we talked about the type 1 case, when you break up an integral into two pieces, and you're looking for whether the original integral is divergent or convergent, if one of these pieces is divergent, then you don't need to verify that for the next piece. Automatically, it means, if one of these pieces is divergent, automatically means that the original integral is also divergent. Okay, so this is the improper integral of type 2. Okay, so let's have a look at some examples of these. I will get rid of that. You don't need that. Suppose we want to integrate this integral from 0 to 1 of 3 over x to the 5 power dx. You can see clearly and immediately that this, if you plug in 0 on the left side of this interval of integration, this integral is, there is a vertical asymptote, right? X can never be equal to 0. Yet on the left or the bottom of the interval, we have 0. So we have a vertical asymptote there. Okay, so note, why don't you pause, if you haven't already forgotten, why don't you please pause the video, go through this, because you've seen that how we approach type 1. So a lot of that technique is also applicable here. But just remember, in type 2, you can't set t to approach, you can't take the limit of the integration as t goes to infinity, but you should take the limit of the integral as t approaches the value of the vertical asymptote. So in this case, 0. So note that x equals 0 is a vertical asymptote. Okay, so then we say that limit of that integral as t approaches 0 from the left or from the right. So we go from 0 to 1 as the limits of integration. So the only way we can approach 0 is from the right side, right? So from the right side, as t goes to 0 from the right side. So this is t to 1 dx. Okay, so now, as you can see, this is simply a 3 times x to the negative 5 power, right? And we can easily integrate this, add 1 to this, we get negative 4, and then divide by the new power negative 4, so we get, so this is what we get limit as t goes to that of minus 3 over 4 times x to the 4th power, and of course the limits of integration are t and 1. Okay, so let's evaluate this quantity and then apply the limit. So we have minus 3 over 4, right? And then minus 3 over 4 times t to the 4th power. Okay, so now if you take the limit of this quantity as t goes to 0, so we have looks like we have a divergent case then. So this first term, it doesn't affect anything, so minus 3/4, then plus 3 over, as t goes to 0 from the right side, this quantity approaches positive infinity, so this whole thing, minus 3/4 plus infinity, is equal to infinity. So integral, so this is, right, so because of that, so this is the, among all the examples we've done, this is the first divergent case. So thus the integral from integral 3 over x to the 5th over 0 to 1 dx is divergent. Okay, so the area, that means there is no solution, because the area under this curve is just getting bigger and bigger and bigger as we go from 0 to 1. Okay, because on the left side, on the left boundary, the curve has a vertical asymptote. All right. So let's do another example. Suppose we want to evaluate this integral from 2 to 3 of 1 over root of 3 minus x dx. Okay, so clearly you can see that the upper limit of the integration, if you plug that in here, we're going to have a vertical asymptote, right? X cannot be 3. So I hope you're pausing the video as you're going through this. Okay, so first note that x equals 3 is a vertical asymptote. That's a signal, that's a clue that we have the type 2 improper integral. Okay, because of that. So now we take the limit. As t approaches that vertical asymptote, right? So as t approaches 3, now from the right or from the left? Notice the limit, the interval of integration. So the only way we can approach 3 is from the left. So from the left, 3 with as we approach 3 from the left of 2 to t of 1 over square root of 3 minus x dx. Okay, so this is once again it's an integral we can evaluate. So I'm going to do it on a piece of scratch paper here. So that integral you can rewrite, integrand I should say, you can write it as 3 minus x to minus 1/2 power, right? Notice by the chain rule we have to deal with -1 here. So, but if you integrate this, you add 1 to that, divide by the new power 1/2, positive 1/2, which would mean you have to multiply that by 2, and then minus again to take care of the chain rule that gives us a -1 coming from this. So it would be -2 times 3 minus 6 to positive 1/2 power. Okay, when we integrate that. This goes back to the, I think we call that power rule, if I remember it correctly, but we're just applying that, that's all. And remembering that we got to watch out, because if you integrate this by the chain rule, you're going to get -1 coming from this negative, and you have to, which balances out with this minus, giving us positive 3 minus 6 to minus 1/2 power. That's why we have this minus here, okay, because of this -1 coming from this x inside the parentheses. So that's our integral, or that I should say the antiderivative. So we have, well, let me rewrite it. I'm just going to add a step here. So 2 to t of 3 minus 6 minus 1/2 dx. And then I'll just write down what I had on that paper. Okay. So we have limit as t approaches 3 from the left. And then we had -2 times 3 minus 6 1/2 power, and then of course going from 2 to t. Okay, so now if we evaluate this quantity, we have limit as t approaches 3 from the left. What do we have? We have t, let me substitute that, x with t, -2, 3 minus t to 1/2 minus this minus and that minus. It'll make it positive 2 times 3 minus 2 to 1/2. Okay, so that's just 2. This piece is just 2. 2 times 1 is 2. But now here, as this quantity approaches 3 from the left, we get 0 here. So this drops out. So taking the limit of this quantity, we have 0 here plus 2 times 1, or 0 plus 2, or 2, right? So we have that. All right, so we have this quantity, and it is not equal to plus or minus infinity. Thus, the integral from 2, 3 of 1 over square root of 3 minus x dx converges. Okay. I cannot emphasize enough to please pause the video as you go through this, okay? And don't spend more than 15 minutes on these examples, but then if you can solve it, take the examples as far as you can within that 15-minute time frame. Hopefully within 5 minutes or 7 minutes, 6 or 7 minutes, you're done. And then unpause the video and compare your solutions with this. But please don't just watch the video without doing that work on your own too. Okay, so now let's, then we have the comparison test for improper integrals. So we should talk about that as well. So a comparison test for improper integrals. So that's a test that tells us whether an integral is divergent or convergent. But this method, this comparison test, relies on us finding another easier function to integrate that is either above or below the integral that we are asked to evaluate for convergence or divergence. Okay, let me repeat that again. This comparison test relies on us finding another curve or function to integrate that is much easier to integrate than the function we are given. And depending on what happens to that function, if it diverges or converges, then we can, by this comparison test, we can make a statement about the improper integral that we have. But the first step in this comparison test is finding another curve, another function that is easier to integrate than the one we are given, okay? Which is, by the way, in some way connected to the integral or the integrand that we have. It has to be connected. It can't be just any function that is easier to integrate. That easier function has to be connected to this more complicated function that we have to integrate and decide whether it converges or diverges. So that's the first and most important step in this comparison test. But the condition is that, okay, suppose we have two functions f of x and g of x that are continuous functions. Okay, not discontinuous, but they have to be continuous functions such that f of x is greater than g of x. Now, we could be given g of x, and it's easier for us to find f of x, or we could be given f of x, and it's easier for us to find g of x. So, but as long as one curve is larger than the other, and both of them are positive, greater than or equal to 0. So the values of functions are positive, as well as the fact that x values, this method, this comparison method is for when x values are positive or equal to 0. So if that's the case, then if the higher curve, that's f of x, right? And on this side, you can see it's infinity. It's approaching infinity. If the high curve is convergent, if this top curve or the higher curve is convergent, then the bottom curve, g of x, is convergent too. Okay? So, in other words, we might have this function g of x that is more complicated than f of x. And then we find f of x, which is a higher curve. And then we evaluate that curve. We take the integral of that curve, which is easier to integrate. And if that is converging, we say, oh, the g of x that we have is also converging. Okay? So that's one. And if the lower curve, g of x, is divergent, if this curve is divergent, right? Suppose we are given f of x, and it's a more complicated function, more complicated improper integral. Then we find another easier one, let's say gx, that is below it. And then we find, after taking the improper integration of g of x, we find out that g of x is diverging. If that's the lower curve, if it's divergent, then the higher curve is also divergent. Okay. And I should add, so this one would be higher curve. Okay, higher curve. So this is, I tried to put this in a note because it's so important, and this is what I said at the beginning of the discussion about the comparison test, is that to use the comparison theorem, we must first find a curve or function that is either higher or lower than the given integrand, whichever is easier to find. So it might be, it doesn't make any difference. It could be the function or curve we're finding could be either higher or below the function we have to integrate. It doesn't make any difference. As long as it's easier, whichever is easier, we find that. So let's look at a couple of examples of application of the comparison test. So in this example, we want to, we want to use the comparison test or theorem to is convergent or divergent. Okay, and here is an example. So we want to arctangent x divided by 2 plus e to the x dx. Okay, let's see. Okay, so notice that this integrand represents a curve, some kind of a curve, right? So and arctangent x divided by 2 plus e to the x represents a curve. So first to find a function that is connected to this, that is related to this function we have, related to our, let me call it, to our integrand, but easier to integrate. Okay, that's our first goal. So in order to achieve that, notice that maybe I should bring back that diagram that I drew here a while back, a few minutes ago. That this red curve is the inverse tangent function, or arctangent, or either this or arctangent of x, right? That's that curve. Notice that over this interval, over the interval from 0 to infinity, or over the positive values, that function ranges from 0 to pi over 2. And pi over 2 is a horizontal asymptote. Okay? So for sure, we know that whatever the value of x over this interval, it's not this quantity, arctangent x, it's not going to be larger than or even equal to pi over 2, right? This, again, this knowledge comes to us from what we did in Math 127, Precalculus 2. So that quantity can never be larger, this arctangent of x can never be equal to or larger than pi over 2, right? So therefore, we can make that statement mathematically and say that arctangent x, I'm using arctangent x because that's what your book used here. They didn't use inverse tangent, so I'm using the same notation. But arctangent x must be less than pi over 2. Okay? Now, pi over 2, pi is simply 3.14. It's that irrational number, right, which never ends, but the first few digits are 3.14159 and so on. So if you take the ratio of that, 3.14159 by 2, you get, I think I did that, you probably get something about 1.57, roughly. 1.6, let's say, 1.5, something like that. So for sure, we don't want to take something decimal, right? It's easier to deal with something whole number. So for sure, that is less than 2, right? Let's round it up to the next whole number. For sure, we know this to be true. Again, going back to this diagram, this quantity can never be equal to or larger than pi over 2. So we know that. Now let's set that. We know that for sure is less than 2. We can do a quick calculation with our calculator and see that that's true. So therefore, and remember, we're doing this to find an easier function to integrate over this interval. That's what we're looking for. Okay. So we can replace this numerator with 2 over e to the x. For sure, that would be a larger function or a higher curve than what we have, right? If I replaced arctangent x with 2, which I know to be larger than that, and I got rid of this 2, and I just kept e to the x. So I reduced, or I reduced the denominator, which means it would increase this quantity. So for sure, that would be a higher curve or higher function values than the one we have, right? So that's what I'm thinking of doing. So it looks like, in this case, it's easier to find the higher curve. If it was easier to find the lower curve, I would do that. But given the arctangent function that we have, it's easy, and going through this process, it's really easy to find the higher curve. It's going to be 2 over e to the x. Okay, so notice that because of this, thus, and because of this is what we are going to say, what I'm about to say, that so arc tangent x divided by 2 plus e to the x, 2 plus e to the x must be less than 2 over 2 plus e to the x, and that must be less than 2 over e to the x. And just think about it conceptually in terms of values overall, right? This is a higher curve than that. This is this function consistently for each value of x. This function is going to produce or output larger and larger values than this function. So this is a higher curve than that. So we found a function that represents a higher curve, and look at that. This is an easy function to integrate. So let's do that then. So now we can say that I'm going to keep the limits of integration is the same, but I'm going to replace this with this higher curve, because I know that if that improper integral converges, then this one will also converge. Okay, so now integral from 0 to infinity of 2, I'm just going to write this as 2 times e to the minus x, right? It's the same thing. Dx is equal to, now this is an improper integral, so take the limit as t goes to infinity of 0 to t, 2e to the, maybe I should put the 2 out, but it's okay. 2 times e to minus x dx, and this is really an easy function to integrate. We can simply write limit as t goes to infinity of minus 2 e to minus x from 0 to t. Okay, all right. So now we can evaluate this expression and then take the limit of that result. We have minus 2 divided by e to t power minus, and then this is just 0, 1, minus 2, like that. Okay, so what do we have? If we apply the limit now, this limit as t goes to infinity, this expression goes to 0, right? So we have 0 plus 2, which is equal to 2. So because the higher curve is convergent, and also maybe I should mention it here. I said it, but it doesn't hurt if I add it here, that this is a higher curve. And by that, I'm referring back to this page when we discussed the comparison theorem or the comparison test. When I mentioned higher curve, lower curve, that's what I'm just saying. And we said that if the higher curve is convergent, then the lower curve is convergent too. In our case, the lower curve is the curve we are given. This is the lower curve. Okay? So the higher curve is convergent. higher function or higher curve is convergent, thus the lower curve, which is what we have, 0 to infinity arctangent is also is convergent. Okay. All right. So that's just one application of the convergence theorem or convergence test. Let's do another example, I guess, of application of the comparison test. Okay, suppose we want to apply the comparison test to this integral 0 to 1 over x times square root of x dx. So notice that for sure x equals 0 is a vertical asymptote, right? But one other thing you should notice here, and this is, let me start the solution here. Note that this function, secant x, is this is from trigonometry, is the reciprocal of the cosine function, right? So let me write this down. Note that secant x reciprocal of cosine of x function, and because for this limit, this boundaries of integration, for this interval, and because for x between 0 to 1, we roughly or approximately have this. So cosine of x is varies between 0.55, roughly 0.55 and 1. We can say that about x values, this cosine function, we can say that about it for x values that range between 0 and 1. Let me see, right? Okay, so that, like that. And then, so because of that, then if within that same interval of x, if secant is the reciprocal of these values, then, so then, thus, or then, secant, over this interval, no matter what value within this range, because secant is the reciprocal of those values, then secant x will always be greater than or equal to 1. Okay, because if you take this end, 1 over 1, reciprocal of that, it'll be 1. That's the minimum value of secant of x. If you take 0.6, that's going to be larger than 1, right? For any value of cosine of x within this interval, which is the result of x varying between 0 and 1, the secant is always going to be either equal to 1 or some larger value. Okay, so secant of x greater than or equal to 1 for x being between 0 and 1. Yeah. Okay. So therefore, so based on that understanding, thus, we can say that that integral, thus this secant squared x, I'm trying to keep everything on the screen. If I sometimes get off, scroll off the screen, I apologize, but like that. Like that. So it's barely visible. So secant squared x over x times square root of x is definitely a larger value than 1 divided by, and this is, by the way, x to 3/3 power, right? I just combined these two into that. So because this secant of x is always equal to larger than 1, so I should make that statement, greater than or equal to 1 over x to the 3/2 power. Okay, guaranteed, because this numerator is always either 1 or something larger. So therefore, this curve, it's going to be a lower curve in respect to this curve that we have, right? So this is going to be a lower curve for us. So lower, easier, let me say this, lower curve which is easier to integrate. Okay. All right. So because of that, then let's integrate this one. Of course, it's going to be, again, it's going to be an improper integral, but we know how to handle that. So now we have integral from 0 to 1 of 1 over x to dx, and this is equal to 0 to 1, of course, x to minus 3/2 dx, and then let's take the limit of that. We take the this time x to be, so t, because this is an asymptote, right? For the asymptotes, we have to take t to go to the asymptote value, x equals 0, in this case from the right, because 0 to 1 is our interval. So as t approaches 0 from the right of this integral, t to 1, like that. Okay, so that's, we can easily integrate this, and this is what we get. We get limit as t approaches 0 from the right, and this add 1 to this divided by the new power, so we get minus 2. So the new power would be adding 1 to that. That would be minus 1/2. So it will be minus 2x minus 1/2 power, and then from t to 1. Okay. So then let's take the limit as, let me move this up a little bit, like that, and then so we have minus 2, that's just 1 to minus 1/2 minus 2 times t to minus 1/2, like that. And that's of course, it's going to drop out as 0, because this is, if you rewrite this with positive t power, in fact, let me do that, even though it's going to take some space. It's okay. So this is just 1, that's negative 2. And then this is positive 2 over square root of t, right? And now if we apply the limit that term drops out. Well, no, sorry, that term would be positive infinity, in fact. So we have minus 2 plus positive infinity, which is infinity. And so for sure, the lower curve, right? The lower curve, which is easier to integrate, is divergent. So let me write that here. Is divergent, thus the higher curve that we have, which was 0 to 1 secant squared x over x square root of x dx, is also divergent. Okay, so this is a couple of applications of the comparison test. So I hope this session was useful. Of course, I plan to do more examples. In addition to these, I'll plan to do more when we meet in the class, and then you can also ask me any questions you have. I thank you for watching this video until the end, and for now, have a nice day, and I'll see you again next time.